of a particle which confined to move along a straight line is given by this position function, and it's also a function of time, whereas it's measured in meters from a convenient origin and t is in seconds. First, determine the time required for the particle to reach a velocity of 72 meter per second from its initial condition at t equal to 0, and the acceleration of the particle when v is equal to 30 meter per second, and then you have to determine the net displacement of the particle during the interval from time equal to 1 to 4 seconds. All right. So because we know this s function, and now we want to know when velocity is equal to 72 meter per second, and we want to determine the time required. So let's use this definition. Your velocity v is equal to ds over dt. So that means we can directly do the differentiation to this position function. So your v will be d over dt to 2 times the t cubic minus 24t plus 6. That will be equal to 6 times the t squared minus 24. Okay? Then we know if velocity is equal to 72, then 72 will be equal to this equation. Then you can quickly determine the time. That will be 4 seconds. Okay? It's quite straightforward. B. If we know velocity is equal to 30 meters per second, and we need to determine the acceleration. So we can still use the definition. So your A will be dv over dt. Or you can directly use the position function when you do the double differentiation. So your A, so now from the previous question, you know our V will be 6 times the t squared minus 24. If you want to determine the A as a function of time, then that will be 12 times t. So from the equation 1, when velocity is equal to 30, then you should be able to determine the time. That will be 3 seconds. Okay? Then you can move on to the second equation, and you plug in the time. So you know the acceleration, 36. That will be meter per second square. See, it's asking about the net displacement. That means it's the position difference between the position at 4 seconds minus position at 1 second. So that means you can directly plug into the original equation and calculate the position difference. Then you obtain the answer. So finally, it's 54 meters. Okay? So it's quite straightforward. All right, let's move on. So let's look at another example. Right now, we're looking at a driver, and she's driving a car, and she applied the brakes to produce a uniform acceleration. That means the AT is always constant along the path. Okay, and her speed is 100 kilometer per hour at A, and 50 kilometer per hour at C, and also the distance from A to C is 120 meter. If the passenger experiences a total acceleration of 3 meter per second squared, the total acceleration means the at squared plus an squared, and the take a square root, that will be for AA. And also the radius of curvature at C is 150 meter. So we need to calculate the radius of the curvature at A, the acceleration at the inflection point B, and the total acceleration at C. Okay. So let's look at all the given conditions. So we know the AT will be always constant. Then at point A, we know VA is equal to 100 kilometer per hour, and also the AA will be equal to AT squared plus AN squared. The square root will be equal to 3 meter per second squared. And we know for point C, VC is 50 kilometer per hour, and low C is 150 meter. And also we know from A to C in terms of a position, it's 120 meter. So based on all this information, we should be able to solve this problem. So first of all, we want to determine the radius of the curvature at A. Okay, so now we know the position difference from C to A is 120. Then we also know the AT is always constant. So based on that, you should be able to uh, come up with these ideas. So for example, your dV over dt, that will be A, ds over dt, that will be your V. So you use the right hand side, you use A divided by BB, that will be equal to this guy, the left hand side of equation 1, divided by the left hand side of equation 2. So you can quickly derive dV over ds will be equal to A divided by B. You move things around, then you can have this, sorry about that, V times the dV will be equal to A times the ds. The reason that I come up with this ideas is because first we know the position, we also know the velocity, and we know the AT. We don't know the AT, but we know AT is constant. Okay, so based on that, we can quickly derive this equation because we can put a constant here. That means we can do the integral. Okay, so from this equation, you know V dV will be equal to A constant plus the ds. Then you do the integral s from 0 to 120, VA to VC. Then, so you know, at the left hand side, that will be 1 over 2 V squared from VA to VC. This A constant, that will be the tangent acceleration, AT times S from 0 to 120. Okay? So from this equation, you can quickly derive your AT. But before that, we have to change the unit from the kilometer per hour to meter per second for convenience. So VA is 100 kilometer per hour. That will be equal to, let me move to here. Then that will be 100 kilometer per hour times hour to second times kilometer to meter. So here, 1 hour is equal to 3600. Here, that will be 1 kilometer is equal to 1000 meter. So use this equation, you can derive VA is 27.8 meter per second. And you can do the same thing. VC is 50 kilometer per hour. That will be half of VA. So you can directly apply to this 27.8. So it's 13.89 meter per second. And from for this equation, 1 over 2 your 13.89 square minus 27.8 square, that will be equal to your 80 times 120. So your 80 will be negative because it's saying it's a uniform deceleration. 2.41 meter per second square. Now we know our AA will be equal to 3, and that's coming from your AT squared plus AN squared. We know the AT, so using this equation, you should be able to derive your AN will be equal to 1.785 meter per second square, right? And your AN will be also equal to your VA squared divided by log A. So your log A will be VA squared divided by AN. Then it becomes 432 meter. So that's for the first question. So the second question is that we want to determine the acceleration at the inflection point B. Inflection, that means the curvature. Curvature will be 0. Okay, curvature will be 0, then that implies your law will be infinity. And if law is infinity, then when you calculate your AN, that will be equal to VB squared divided by law. Law is infinity, then AN is 0. So your AB will be equal to your AT squared plus AN squared, take a square root, you only have the AT, right? So it's 2.41 meter per second squared. That's only for the magnitude. If you want to present or you want to include a positive or negative, then that will be negative 2.41 meter per second squared because it's a deceleration. It's quite straightforward. Problem C, let's move back. We want to determine the total acceleration at C, and let's look at the condition. We know the VC, we know the log C, so that means we can determine the AN, and we do have the AT, so we can determine the total acceleration at point C. So the AN here, that will be VC squared divided by log C. So VC is 13.89 squared divided by log C, that will be 150 meter. Then it becomes a 1.286 meter per second squared. Present this AC in a vector form, so that will be negative 2.41. That's AT, it's a constant. So your UT plus 1.286 UN. The magnitude, you do square summation and take a square root 2.73 meter per second square. Okay, so it's quite easy. All right, let's look at another example. Now uh, we have this slotted arm, and it can rotate by itself. We have a particle B that can move around uh, in that slot. So now, in terms of this theta, it's a function of time, and also the power screw in the arm engage the slider B and control its distance from O, the origin, to R is equal to also a function of t. Now we want to calculate the magnitudes of the velocity and acceleration of the slider for the instant when t is equal to 3 seconds. So basically, right now we move to the cylindrical coordinates. Then you have to know how to derive your velocity and acceleration in terms of the r and theta. Okay. So before we're doing anything, let's derive all the equation together again. So basically, the r is equal to r times ur. That's a very basic definition for the cylindrical coordinates. Then u of v will be, you apply the derivative to this r, that will be r dot times ur plus r times ur dot, right? Then ur dot, you will get your theta dot, right? Times u theta. Then acceleration. So you have some components related to ur and some components related to u theta. So first of all, you apply that to this r dot, r double dot. And also you apply the dot to u theta. So it becomes negative. You get one more theta dot. So theta dot squared. Then you apply the dot to ur. You get the r dot, theta dot. And also you apply the dot to this r theta dot. You apply to this r. So 2 times. Then plus you apply the dot to this theta dot, theta dot dot. So in this equation, our first step is that you want to determine your r dot, r double dot, and theta dot, and theta double dot. Okay, the only condition we know is t is equal to 3 seconds. So starting from this given conditions, theta is equal to 0.2 t times 0.02 t cubic, and your r is equal to 0.2 plus 0.04 t squared. So we know, or just quickly write this equation. Your r dot with respect to time, so 0.08 t, r double dot is constant, 0.08. Your theta, I just rewrite this equation. So your theta dot will be 0.2 plus 0.06 t squared. Theta double dot, that will be 0.12 t. So when t is equal to 3 seconds, then you obtain your r is equal to 0.6 meter, r dot is 0.24 meter, r double dot will be 0.08 meter per second square. Sorry about that, meter per second for r dot. Your theta, that will be equal to, you just plug in this 3, you obtain 1.14 radian. Your theta dot will be 0.74 radian per second. Theta double dot, that will be 0.36 radian per second squared. Okay, so you know velocity will be equal to, so you can scroll up, then we know that will be r dot times ur plus r times theta dot u theta. So that means it will be 0.24 ur plus r times theta dot, that will be 0.414 meter. So let u theta. So the magnitude of velocity will be equal to 0.24 squared plus 0.414 squared. Take a square root, you get a 0.479 meter per second. The same thing for your A. If you square up, you will see that will be r double dot minus r theta dot squared times ur plus 2 times r dot theta dot and plus r theta dot u theta. So it will be equal to 0.227 ur plus 0.557 u theta. Again, if you want to calculate the magnitude, you just use this 0.227 squared plus 0.557 squared, like a square root, so you can get this 0.601 meter per second squared. Okay, it's also quite straightforward. So the very basic thing is that you know how to derive the velocity and the acceleration from the position vector. So especially for the cylindrical coordinates. Okay. All right. Next example is about a kinetic problem. So it's saying a man with a 75 kilograms standing on a spring scale in an elevator. During the first 3 seconds of a motion from rest, the tension T of the cable is 8,300 Newton. Find the reading R of the scale in newtons during this interval and the upward velocity V of the elevator at the end of the 3 seconds. And the total mass of the elevator, man and scale, is 750 kilograms. So basically, in this problem, we treat the elevator, mass, and scale as a single particle. It's a system. Then afterwards, we can move on to the man itself. Then based on that, we should be able to determine the scale reading, and also from the derived acceleration, we should be able to calculate the velocity. Okay. So first of all, we start with the free body diagram. That will be equal to kinetic diagram. The free body diagram is the whole system. You get the tension T here. That will be equal to 8,300 Newton. From the self wet, that will be W is equal to 750 times 9.81. So it's 7360 Newton. And then this guy is the single particle with acceleration. We define its upward a y. So you can determine the equation of motion for this system. So your sigma Fy, that will be equal to m times ay. We determine the positive is upward. So your T minus W, that will be equal to your mass times ay. So your T is 8,300 minus the W, 7,360. The mass, remember, we consider the whole system is 750 kilogram times ay. So your ay will be equal to 1.257 meter per second squared upward. Then now we break down to that man only. So again, we go back to the free body diagram. That will be equal to kinetic diagram. The man here, and the man is standing on a scale, right? So it will have the reactional force coming from the scale. So that's the normal force R, and it has its own weight. It's a 75 kilogram times 9.81. It will be 736 Newton. It will be equal to this guy with the same acceleration. So we only consider the vertical equation, the vertical direction. So your sigma Fy will be equal to n times Ay. Again, positive will be upward. Then your R minus this the self weight will be equal to 75 kilogram times this Ay. So R will be equal to a 30 Newton. Okay, so that's the scale reading in terms of Newton. 4, we want to determine the velocity, and it's saying the acceleration will be constant, right? So that means we can use dv over dt will be equal to AC, and this AC will be that AY we just calculated. So your dV will be equal to your AC times dt. From 0 to 3, it's given by the problem, and starting from rest, so 0 to the curve B here. So for the left hand side, you obtain its V. For the right hand side, that will be your 1.257 T from 0 to 3. Then 3.77 meter per second. Okay, so let's quickly review this problem again. In the very beginning, we considered all the things together and treat all these things as a single particle. Okay, then using this free body diagram equal to kinetic diagram, we can obtain the acceleration. Then once we have the acceleration, we can go back and consider the man only. Then use this acceleration and also the free body diagram equal to kinetic diagram, we can derive the equation of motion. So in this equation of motion, we should be able to determine the reactional force from the scale to the man. Then we can determine the reading. Also, because we know this acceleration will be constant, then using the definition dv over dt is equal to acceleration, we should be able to determine the velocity, the current velocity or the velocity at 30 seconds. Okay. All right, let's move on. The next example is that a 1500 kilogram car enters a section of a curved road in a horizontal plane and slow down at a uniform rate from a speed of 100 km per hour at A to 50 km per hour at C. The uniform rate means your AT is constant. Okay. The radius of the curvature at A is 400 meter, at C is 80 meter. Determine the total horizontal force exerted by the road on the tires at position A, B, and C. And B is the inflection point. That means the curvature is infinity. The AN at B is 0. All right. So, the first of all, now if we do the free body diagram at each point, then that will be, here is the car. Then the force from the row will be somewhere. Let's say it's going to be this way. That's your F in the horizontal plane. That will be equal to the mass of the car. Then you break it into, for example, your AN and AT. Okay. So from this free body diagram is equal to kinetic diagram, then you can have your two equations. Sigma Fn, that will be equal to m times An. Sigma Ft, that will be equal to m times At. Then now we don't know any Fn or Ft at any points. We don't know the An or At at any points. Now the only thing we know is velocity at A, velocity at C, and we know the curvature, the radius of the curvature at A and at C, and we know the At will be a constant, and we know the mass of the car. Okay, so for this problem, we have to start with the motion variables. So we know At, sorry about that, At is constant, and we want to determine At if possible. Okay, so again, we know dVt over dt will be At, and also know from this graph, we know from point A to point C it's 200 meters. So ds over dt will be equal to Vt. Then you use this relationship. You just use the left hand side divided by left hand side, right hand side divided by right hand side. You should be able to obtain this Vt dVt over ds will be equal to At over Vt. You move things around, so Vt dVt will be At times ds. So Vt dVt, your At times ds. We know the velocity Va to velocity Vc, and S ladder will be from 0 to 200. And also At is constant. Then we can have 1 over 2 V squared from Va to Vc will be equal to At times S from 0 to 200. Right? So you just plug in all the numbers, you should be able to determine At will be equal to 1.447 meter per second squared. So third, let's consider at point A, and we have, let's say this equation is 1, this one is 2. So for 1, you know, your Fn from the tire, from the road to tire, Fn will be equal to your mass 70, not 75, it's 1500 kilogram times An. An will be equal to your Va squared divided by log, because the Va provided must be along the tangent direction, right? So the Va will be the Vt. You just plug in the numbers, you should be able to obtain it's 2890 Newton. Ft, if you use the second equation, that will be equal to, again, the same mass times your At. Then it will be 2170 Newton. So the total force in terms of the magnitude, then you just use this to do the squares, take a square root. Okay. At the point B, for Fn along the normal direction, because law, the curvature will be 0, the law will be infinity, and your An will be 0. That means your Fn is 0. For second equation, along the tangent direction, your FT is still the same. 1500 times your AT will be still 2170 Newton. So your FB is still the same as the FT. At point C, for the force along the normal direction, it will be this mass times AN. AN will be equal to your VC squared divided by log C. And you know the velocity and the radius, so you should be able to obtain this Fn 3620 Newton. For Ft, because your AT is constant, so this Ft will be equal to that one at point C and also the one at point A. So it's 2170 Newton. So for Fc, you can do it quickly. Plus 2170 square root, so it's 4220 Newton. Okay, it's also quite simple. All right, let's move on. Now we have two airplanes A and B are flying with constant velocity at the same altitude. The positions of the planes at time t equal to 0 are shown in the following figure. So basically they move in a straight lines, but two different directions. And to determine the velocity of the plane A related to relative to B, the position vector of A relative to B is a function of time, and also the minimum distance between the planes and the time when this occurs. So, so first of all, so for the question 1, you have to know, now it's saying we want to know VA, that will be equal to VB plus VA related to B, right? So then in order to calculate this VA related to B, then we have to define these two in absolute coordinates. Okay, so now we would like to present VA and the VB in terms of I and J in terms of the XY coordinates. Okay, so your VA will be 580 times the unit vector, 580 times, it's for this triangle, it's 3, 4, and 5. So in terms of x, it's 40 kilometer divided by 50. In terms of I, the same thing. It's 30 divided by 50 in terms of J. So you can quickly derive VA is equal to 464I plus 348J. Remember, you do have unit. That's a kilometer per hour. VB, you can do the same thing. It's a 260 kilometer per hour times the unit vector 260. Right now, you have to be very careful because for x, the direction is toward the positive x, but y, it's toward the negative y. So it will be positive for I, negative for J. All right, and along the x direction, it will be 40 divided by 50. For y direction, it's still 30 divided by 50. So after the calculation, it's 208I minus 156 J in kilometer per hour. So your VA related to B, that will be your VA minus VB. So you can quickly obtain the answer. then kilometer per hour. Okay. And again, for a 2D problem, probably you can answer by this I and J, or you can use a magnitude and the direction to present this vector. So the magnitude of this relative velocity will be, it's quite straightforward. So it will be 565.3 kilometer per hour, and the angle. So the way we determine the angle is that it's positive x, right? From this positive x, you do the counterclockwise to the current vector. So this theta will be your arctangent, the y component divided by s component, right? So it will be your arctangent, 504 divided by 256. Okay. Then it will be, check, it will be 63.07 degrees. Okay. Then second, we want to know the position vector of A relative to B as a function of time. And because in the problem statement is saying these two airplanes are flying with constant velocity, okay, along that vector. So now let's go back to this equation. So basically VA is constant, VB is also constant. So that means VA related to B is also constant. So if we want to know the position vector of, let's say, that's SA related to B, or you can use a position vector R to present it, then basically we know VA related to B is constant. Then we know VA related to B is this one. It's constant, so we can use the definition. dr over dt will be v, and then you can also put the vector form. So your r will be, you do this vab dt, you do the integral, right? And also it's the from rest, so we don't need to consider t is equal to 0, right? Just a second. Let me rewrite this equation, and we go back to the problem statement. In terms of the r, from very beginning, it's showing in this figure. So in the very beginning, you do have the relative position, right? So from this equation, you move things around, then you will have your dr will be equal to your VA related to B times the dt. And then we put the integral to both sides. Then that's from 0 to t. It will be from the r0 to current r. So your current position A related to B will be this BA related to B times t plus r0. Okay, where your r0 is So you go back to the problem statement. It will be RA minus RB, right? RA is at the origin. RB is 30 kilometer uh, above this A, right? So it will be your RA minus RB in the beginning. RA is 0I plus 0Z. Your RB is 0I plus 30Z. Then this relative uh, position will be negative 30Z. So this equation will become so 256 Ti plus 504 T minus 30 J, right? Okay. Then you do have the unit kilometer. All right. Third, we want to know the minimum distance between A and B and the time when it occurs. So that means we want to minimize the distance between A and B. So you can further extend this equation to you want to minimize this A related to B squared. So your RA related to B squared will be the X component, you do the square, the Y component, you do the square, right? You just populate all the terms. Then let's see. So for this equation, if you partial this guy from the calculus, we know if you partial this guy with respect to the variable, you can have the and make this equation equal to 0, then you can obtain the peaks, right? Then if the coefficient for the t squared term is positive in this equation, then you do have the minimum, right? So that means these peaks will be minimum. Okay. So based on this equation, we know it will become 2 times 256 t. However, you have to do one more, 256 plus 2 times 504 t minus 30, and you keep doing the differentiation to the t component, 504, and the max is 0. Then you get the t is equal to 0.04732 hour, or you can convert it back to second, 170.3 second. Okay, and your S minima will be, you use this number, plugging back to 1 when t is equal to 0.04732. And then for the equation 1, you have to do the square root. So finally, you can obtain this 1359 kilometer. Okay, then that's all we have today. Thank you.